Okay, so let's see, logarithms, we're going to start with the definition of a logarithm. Logarithms have been around since, I think, about the 1500s, if I'm not mistaken. They've been around a long time, and part of where they came from was ways to make calculations simpler, and that's kind of what they were used for early on. So what a logarithmic function is first of all, you've got to understand that it's really just a way of rewriting an exponential expression. All right. So first thing I want to talk about is just the different forms. So this is called the log form. Whenever you have this, you read this as logarithm base b of a number is equal to y. And that's the equivalent to this exponential form like that. So the first thing you've got to learn how to do with a log, and it's probably the most important thing to learn, is how to change these from one form to the other, because everything that you do kind of revolves around that idea. So the idea is the base is the b. So when you change it to this form, well, then the base is just going to be the same there. It'll be the base, the exponent. The answer to a log, I always try to stress this, the answer to a log is an exponent. Okay, that's what a logarithm is it's another way of writing an exponent. All right, so whenever you do this and change this, that exponent will be y like that. So what we're going to do, first of all, is just kind of look at how you rearrange these forms. We'll talk about some of this stuff in a little bit here. The domain of a log is positive numbers. Okay, you can only do a log of a positive number. I'll talk about why that is in a little bit here. So for now, it only makes sense to take logarithms of positive numbers, and we'll get to that in just a minute here. The other thing is a base 10 log. You usually just write log. That's the button that's on your calculator. That stands for a base 10 log. So if you've got log, that's always going to tell you it's a base 10. And then if you have ln, a base e, that's called the natural logarithm. So ln just means that you have a base e. Okay, and we talked about e in the last section a little bit when we were working with that then. Okay, so let's start this way. Let's go down and let's just rearrange these things in the form. That's the first thing you got to learn how to do. All right. So it's actually real easy. These are all in log form. They all have a logarithm in it. So what you say is that's the base, and you don't have to necessarily write my words down on this. I'm just explaining what everything is. That's the base, that's the exponent. So what we would say is 10 to the third is equal to 1,000. Okay, that's how you change that over. So it means the same thing. If you're asked for a base 10 log of 1,000, it just means what power of 10 is 1,000. Okay, a logarithm is an exponent. Okay. Same thing on this one. Now this one, anytime you see ln, you need to understand that that's understood to be a base e logarithm like that. Okay. So then again, this is your base. That's your exponent. So when you write this down, you just say e to the 9th is equal to x to the 2nd. You're not solving that equation or anything. You're just rewriting that as a exponential form. Okay. What base did I say log was? Base 10. Okay, so this one, you can do this all in your head, but it's just understood to be a base 10 log. And then this goes like this. Okay, this is the base, 10's the base, the z is the exponent, so it's equal to x plus y. All right, so that's the first thing that you want to know how to do is rearrange the log form to exponential form. Okay, usually nothing to that. We're students, and that's one of the most important things to learn about logs is how to rearrange these forms. Okay, right? We'll do these backwards. On example 2, these are all exponential expressions. So it's always kind of goes like this. The base is the 2. The exponent is the answer to the logarithm. So I just say log base 2. When you do a log, be sure that you do that subscript like that so it's real clear. The answer is the exponent. Then the 8 is the argument of the logarithm. That's what we're taking the log of. So if you're doing a log of 8 of base 2, you're just thinking what power of 2 is 8? Remember, a log is an exponent, okay? Right, this would be the same way. This is the base. That's the exponent. So you would just say log base 10. The answer is the exponent. Then you have 10,000 like that. So that's how you'd write that in log form. You can write it that way. It's not wrong to write it that way, but you can write it in the abbreviated form. Log of 10,000 equals 4, okay? And your calculator will do, it'll do base 10 and base e, and there's another place on your calculator that'll allow you to put any base in anyway. So if I did log of 10,000, you're just figuring out what power of 10 is 10,000. Well, 10 to the 4th is 10,000. So that's what that's doing, okay? And the next one goes like this. This last one, you would have logarithm with base e. The answer is the exponent b of a like that. So you just write the log. You just write that as the abbreviated form. You say ln of a is equal to b like that. Okay, so that's the first thing you got to be able to do with logs, is just be able to change them back and forth into those two forms. Okay, any question about that so far? Okay, you'll see logs, in calculus quite a bit, and you see it quite a bit like in finance. You see it in chemistry. If you've taken chemistry or will take it, you'll learn about it. I think it shows up in pH and things like that. It shows up in earthquake, Richter scale, all kinds of things like that. Okay. All right. So the next page, what we're going to do is evaluate a log. And these are all designed on this page so you can do them in your head. Okay. And we're going to focus not on a calculator on this. We're just going to do these in our head, basically, when we can. So this is kind of a strategy. Now, you can do a lot of these just in your head. The meaning of this problem, this is a method that you can do if it's helpful to you. You can always just take the expression and set it equal to x, okay, if you want to. Okay. Then you can write it in exponential form, which would say 5 to the x equals 125. And these problems are designed so you can do them in your head, or maybe you kind of play with the calculator a little bit. So what is x in this problem? What power of 5, what do you raise 5 to get 125? To the third. It's the third, right, okay? So the answer would be 3. So when you're looking at a logarithm in your head, you're just saying, what power of 5 is 125? The next one is easier to do. This is saying, what power of 9 is 9? So what is that? That's 1, right, okay? All right, so the ones that you can do in your head, you can just write your answer on. So I'm going to kind of show you a strategy. Set it equal to x, write it in exponential form, and see if you can do it in your head, okay? Most of the time, you'll be able to do that fine, okay? All right, the next one, I'll do the same thing. Log base 3 of 1 equals x. So what this means is, what do you raise 3 to get 1? So what's that? 0, right, okay? Anything to the 0 power is equal to 1. All right, so see, those first 3 problems are done the same idea. Your answer is an exponent. That's what you want to get straightened out when you're doing this then. Okay, this next one, we'll look at this the same way. This is log base 10 square root of 10, set it equal to x, okay? And then you just write in exponential form, so that would be 10 to the x equals square root of 10. So you know what that is?
Negative 2.
What?
Negative 2?
No. How do you rewrite a square root and an exponent? You guys remember that?
10 to the 1/2.
1/2, there you go. It's 1/2 power, okay? So the idea, so that would be, you got to remember that 10 to the 1/2 power is the same thing as the square root of 10, okay? Now you'll do that kind of stuff in calculus all the time. You'll work with changing radicals to fractional exponents like that. That's the idea. And you can do that in your head, but the other thing that you can do is you could write this. You could just change that square root of 10 to the 1/2. And then it's kind of like what we're doing at the end of the last section. I said if the bases are the same, then so are the exponents. Okay, so when these problems get a little bit more complicated to manage in your head, you're going to use that idea that we did at the end of 4.3 quite a bit. Okay, any questions so far? Okay, so you got to understand exponents real well to understand logarithms, because that's what you're dealing with. Okay, all All right, let's do this one. This one's, it depends on your skill, whether you could do this in your head or not. I'm going to start this the same way. I just set it equal to a variable x. Then I'm going to write it in exponential form. So that'll be 5 to the x equals cube root of 25. Okay, now what you want to do on this is anytime you have a radical, you want to write that as an exponent. So write that as 25 to the 1/3 power. Okay, like that. All right, now this is identical to what I was showing you beginning of class at the end of 4.3. You want to make those bases the same, don't you? So what do you do with the 25? Make it what? 5 to the second, right? Okay, so what you'll have is this will become 5 to the x. This will become 5 to the second to the 1/3 like that. Okay, and what you do is when this situation arises, you're multiplying those exponents. So you're just doing 2 over 1 times a third, which is 2/3. So what you would end up with then is you would end up with 5 to the x equals 5 to the 2/3. So what's the answer to the problem then? What is x? 2/3. It can't be anything else. So the idea is if the bases are the same, so are the exponents. Okay, so that one right there is harder to do in your head. Okay, just because you've got to kind of rearrange things a little bit to be able to figure that out. Okay, all right. The next one, we're going to learn properties on this eventually. We're going to start this the same way. I would recommend on an ln, just write it as log base e of e to the 4th. That's what that problem's really saying, and then we're going to set that equal to x. Okay, and this one's real easy to interpret once you write this in exponential form. So in exponential form, you would say e to the x power is equal to e to the 4th. All right, so what does x have to be? 4. It can't be anything else, okay? Because again, the idea is if you establish that the bases are the same, then the exponents have to be the same. So that would be 4. You're going to learn a property that's going to say on this, if you had like ln of e to the 10th, the answer is 10. There's properties and little shortcuts you can do on logarithms once you kind of learn the properties. But right now we want to analyze each situation and try to figure it out logically. Okay, all right. Okay, next one. This one's also a little hard to do in your head unless you're really, really skilled with exponents and understand how exponents work. So this is log base 1/3. A base can be a fraction, so you set that equal to x. Okay, now when we write this in exponential form, you'll have 1/3 to the x is equal to 27. Okay, and again, this is exactly like the problems we were doing at the end of the last section. What do you think I should do to the 27? Got to write it as a power of something. What do you think? 3 to the 3rd, right? Okay, the reason 3 is because there's a 3 there. So you could write this left side as 1 to the x over 3 to the x. Like that, okay? And then you can write this side as 3 to the 3rd. See, ultimately what you're going to do is 3 to a power equals 3 to a power, and then the exponents can be set equal to each other. Okay, we said that 1 to any power is 1, so that will give 1 over 3 to the x equals 3 to the 3rd. Okay, what do I need to do with that 3 to the x? I need to move it to the top. We did that on a couple of problems earlier today. So that would be 3 to the negative x. The exponent changes. That's equal to 3 to the 3rd. So what you can do now is those things get set equal to each other. So what you would have is negative x equals 3. I think you can solve that equation if you want to by either multiplying or dividing by -1. So you would end up getting x equals -3 would be the answer to that problem. Okay? All right. I'm going to check this one. I think that's worth doing. I mean, if students would take the time to do this on these problems, they would ultimately, to me, understand logarithms better. So what I'm going to do is just take the problem, log base 1/3 of 27 equals -3. And you can do this without a calculator. The idea is you would have 1/3 to the -3, and you're going to see if that's 27. Okay, here's how this works, and it's not that hard. you would do 1 to the negative 3 over 3 to the negative 3. Well, you want to make both of those exponents positive, so you could do that by switching the order they are in the fraction. Is that going to give you 27? Indeed, okay, because 3 to the third is 27, so everything works out great, okay? That's the idea. You can do that on every one of these problems if you want to, and it would help you quite a bit to take the time to do that a little bit on these problems. All right, so that kind of gives you an idea of how you work to evaluate a logarithm to begin with. You're wanting to try to do these things logically, just by working with the basic definition of a logarithm. Any questions so far? Okay. Logarithms are a problem area for lots of students. We see that a lot when we teach calculus. All right, next thing I'm going to go through is the domain of a logarithmic function and kind of how we do this. And with this, first of all, is I want to just show you why you can't do a log of a negative number. I'm going to first of all do this example. I'm just going to pick a base like base 10 of 0. Okay, this makes no sense. Here's why. If I set this equal to x, like I was doing the last problems, I would have 10 to the x equals 0. Okay, can you think of any number that you raise to, anything that you would raise 10 to that would ever give you 0? There isn't such a thing. Okay, the thing is, if you did 10 to the 0, that's 1, so that doesn't work. If you did a negative exponent, that's 1 over 10 to the first, so it's impossible. You can't take a number and raise it to a power and get 0. You never can. So you can't take a log of 0. You also can't take a log of a negative number. Let me just pick a negative number like negative 1. Okay? If you did this, you would have 10 to the x equals negative 1. That also is impossible. So the only thing that makes sense is to do a log of a positive number. Okay, so that's what you always want to realize when you're dealing with logs is that number m has to be a positive number. It can't be anything else. All right, that's real critical to understand that. So when you do a domain of a log function, these are all just different types of log functions. What you're always going to do is look at this part that we call that the argument. And what you do with that is you just set that greater than 0. And then you solve that inequality using whatever all types of skills we've learned this semester on solving inequalities. So this one's real simple. You just subtract 2 from both sides. So you would get x is greater than negative 2. So the domain, you could either write this as set of x such that x is greater than negative 2, or you could write it in interval notation as negative 2 to infinity like that. Okay, so we're going to take this same strategy on every problem that we're doing with domain on this. And then the idea with this is actually one you could graph on the calculator. So I'm just going to put this in. We had put in ln of x plus 2. You can put it in if you want to. You can just watch what I do. If I do a standard window, what you'll find is there's nothing below negative 2. Okay, so if you looked at your table on here, you'll start seeing a bunch of errors once you get to negative 2 and below. Okay, that's what's going to happen on that. So basically, the graph of this logarithm only is for numbers bigger than negative 2. Okay, and you can verify a lot of these things graphically when you do this then. Okay, all right, that's probably the simplest variety. The next one, you just look at that. You do the same thing. You just say 1 over x plus 4 is greater than 0. All right. Now, sometimes students kind of get mixed up how they do their inequalities. The first example is what we call a linear inequality, and you just solve it. You isolate x. This is a rational inequality. The way we learned how to do this was we learned how to make a sign chart, which is what I'm going to do. Okay. First of all, can you tell me where the vertical asymptote on 1 over x plus 4 is in your head? X equals negative 4, right. Okay, so you're undefined at x equals negative 4. And you don't have any x-intercepts or anything on this. So like if you set the numerator equal to 0, you don't get any x-intercepts on that. So what I'm going to do on this is just put -4. Okay, that's where my asymptote is. And then I'll just do test values. Take a number bigger than -4, like 0. Then you'd have 1 over 0 plus 4. That would be positive there. If you took a test point smaller than -4, like say -5, you would have 1 over -5 plus 4. Well, that's a negative number like that. Okay, so what am I looking for? Where it's positive or where it's negative? Where it's positive, right, because what I'm doing is I'm setting it greater than 0. So that means that what would happen is, graphically speaking, you would be like parenthesis and then to the right of that. Okay, so that would be your domain. So your domain could be written as set of x, x greater than -4, or you could write it in interval notation as -4 to infinity like that. So see, that has to be done with a sign chart. Okay, I mean, you can't isolate x by itself on that because it's a rational function. You could also graph that, and I think that'd help you do that as well. We learned how to look at these things graphically as well. Okay, all right. The next problem, we'll again just work this out the same way. Just look at the argument, and we know that this thing right here has to be greater than 0. And always greater, not equal to 0. It's got to be greater than 0 like that. Okay? This is another example we learned of how to do a sign chart on. This is a polynomial inequality. So when you do a polynomial inequality or a rational inequality, you got to just look at numbers on a sign chart. So first of all, the only 0 on this would be x equals -1, because it's already in a factored form. So on the sign chart, we would just look at x is -1, and then we'd do test points around that and just see what we get then. Okay, so if we take a number bigger than -1, say like a 0, you would have 0 plus 1 to the second. That's a positive number, okay? If you take a number smaller than -1, like -2, you'd have -2 plus 1 squared. Well, that would also be a positive number, because anytime you square any number, you're going to get 0 at the smallest, so it goes like that. Now, you have to be really careful about this. We're looking at where this is positive. And if you did a graph on a number line, it would be all the numbers bigger than -1 and all the numbers smaller than -1, but it couldn't be -1, okay? Because if x is -1, then you're equal to 0. So your domain, we would have to say either set of x, x less than -1, or x greater than -1. It's just every number except -1. And then in interval notation, you could say -infinity to -1, union -1 to infinity like that. Okay, and that one would just be the only number that doesn't work is -1, because if you plugged in -1, you would really be doing the log of 0. You can't do the log of 0. You can't do log of 0 or log of a negative number. Okay, so see, I did the same approach on all those problems. Argument greater than 0 and solve. Okay, the background for solving those inequalities, we've done every one of those cases so far. Okay, and don't forget about your sign charts, because you got to do those sometimes. All right, any questions about that? So far, okay? Okay, all right. Okay, now we're going to get into the graphing. Graphing sometimes is kind of challenging for students on this. If you do this a certain way, then it's not too bad. So I'll try to kind of teach you how to work with the exponential form, and we're going to learn the connection between a logarithm and an exponential anyway as we're doing these. So to begin with, what we're going to do is we're going to graph two things. We're going to graph this first, and we learned how to do that. That's like in an earlier section. Exponential functions tend to go like that. They tend to start and then they go to infinity like that, depending on what the value of that base is. So we're going to graph this, just make a table of values. So we're going to do 10 to the 0, 10 to the first, 10 to the second, and just work all those things out. This is something we've done before, okay? So if you work this out, let's see, 10 to the, anything to the 0 is 1, anything to the first is itself, and then 10 to the second would be 100. And then what's 10 to the negative 1? That's 1 over 10, right? That's 1 over 10. How about 10 to the negative 2? 1 over 100, okay? So let's just plot the points that'll fit on the graph. So we'll have 0, 1, then we'll have 1, 10, like that, okay? And I'm going to have you label probably these 2 points. These are the important points on this. And then you can just sketch that in like that. And remember, the way this goes is you're approaching the x-axis, but you never reach the x-axis. So that would be the graph of y equals 10 to the x, okay, like that, all right? So when I do the table for the logarithm, I picked certain numbers on purpose that I want you to see, all right? So that's an exponential function. Now when I do the log function, I didn't just pick any old number. The thing on this is, first of all, x has to be positive, so I had to have positive numbers there. Can't use negative numbers when I'm looking at a log. So I'm going to start, and you'll probably kind of see why I'm picking the numbers I am, hopefully. Let's start way down the bottom here. Let's do log base 10 of 10, okay? Now you want to get to a point where you can do this quickly in your head. This is just saying what power of 10 is 10. So 10 to what power is 10? 1. 1. So that's going to be a 1, okay? All right, don't use your calculator on that. Just do that in your head. Okay, so we get that. All right. Forget the 2. The 2 doesn't make that much. I mean, if you did log base 10 of 2, then the question would be what power of 10 is 2? I don't know. It's decimals. You don't know that. Okay, so let's just leave that alone. Let's go to 1, though. If I do log base 10 of 1, then you can do this in your head also if you understand logs. So what do you raise 10 to get 1?
0.
0, right. So that one is 0. Right? So we have that. All right, and then let's move on to this next one here. So this next one is log base 10. Now 0.1 is really 1/10. Okay, so ask the same question. See if you catch on to this. What would you raise 10 to get 1 over 10? Negative 1, good. Okay, that's how the negative exponents work out. Okay, good. Okay, so we got that. And then the next one, 0.01 is 1 over 100. What would that be? Negative 2. Okay, all right. So now what I want you to look at is I want you to look at this table and kind of show you what happened here and see if you see anything, okay? We have 1, 10, 10, 1. We have 0, 1, 1, 0. Everything's backwards. What does that mean? What did we learn about that? That's an inverse, right? So these are inverses of each other, okay? So that's what you're going to expect to happen on a logarithm is they're going to be inverses. So let's just plot some of these points. Now we have 1, 0, and that's a good point to label. Then you got 10, 1, so over 10 up 1. And then the log will kind of go like this. It'll go like that, and then it will approach the y-axis. So it's kind of like an asymptote like that. Okay, so that's the idea. The other thing that we learned was it's symmetrical about y equals x. And y equals x is just like a 45-degree angle, a straight line like that. And we learned when we were talking about inverses last week about how the graphs are symmetrical about that line. All right? So to me, one of the best things to do, if you're going to draw a graph of log base 10 of x, you probably ought to just graph out 10 to the x because it's easy, and then just flip all the points. Okay? And then that way, you've got your table. You want to use these numbers backwards on that because we know it's an inverse. Okay, so that's my suggestion is when you do a logarithm, do the exponential and then flip the points. Okay, it's easier that way. Okay, any question about that? Okay, all right. Okay, so we're going to look a little bit at down below here. We're going to work a little bit more on graphs here. But one thing that we want to know is a log is an inverse of an exponential. And that's what I just showed you on that example. This is a log. Its inverse is going to be b to the x. Okay? And like we learned with inverses, the idea is the domain of a log turns out to be the same as the range of an exponential. Okay? All right? And that's because you're doing inverses. And then the range of a log turns out to be the domain of the exponential. So you're flipping the variables, so domain turns into range and range turns into domain. That's the idea, okay? All right, we're going to work a little bit on graphs here, the first part of class here. So let's go to the next page, and I'll do the same thing on E, and then we'll do a little bit with transformations, not too much though. Okay, so this one, what we're going to do on this is we're going to graph, ultimately we're going to do the graph of ln of x, okay? And ln of x, that just means log base e of x, okay? So that means its inverse is e to the x. Just like the last problem, log base 10x, 10 to the x is the inverse, okay? So it's going to go like this then. So we're going to fill out this table right here, okay? Just do these. So we've got like e to the 0, e to the first, e to the second like that, okay? And then anything to the 0 is going to be 1. E to the first, remember, e is about 2.7. We've learned that. E to the second, if you took your calculator, if you needed to, you can go like this. You can go second ln to get the e key to come out. So if you do e to the second, it's like 7.4, I think, approximately. So I'm just going to use about 7.4 there, okay, like that, okay? If you did e to the negative 1, that would be 1 over e to the first. If you did e to the negative 2, that would be 1 over e to the second like that, okay? So we're just going to estimate these points. So let's just plot these points. So we have 0, 1. And then we have 1 over 1 and about 2.7, just estimate. Then over 2 and up a little over 7. So the graph of e to the x is going to be this graph. Okay, that's your exponential function like we've learned earlier. Okay, so that's how that goes. Now what we're going to do on this table is real simple. Okay, all we're going to do here, we don't even need to work this table out. What do I do with all the points since they're inverses? They just all go backwards, don't they? Okay, so what you're going to do here, just change all these things, okay? Instead of saying 2e squared, we're going to say that will become e squared, and then that will become 2, like that. The next one will be 2.7 or e and 1. Then the next one will be 1, 0, and then 1 over e negative 1, and 1 over e squared negative 2. Okay, you know they're inverses, okay? That's the idea. So if we plot those points, then we would get a pretty accurate graph on this then. So basically you would have the point 1, 0. This point E1 is really about 2.71. So you just move over like this and approximate that. E to the second we said was about 7.4. So this point's about 7.42. So if you go over 7.4 up to it goes like that. So this would be the graph of ln x like that. So it's just like the last problem, except this is base e. Okay, you do these exactly the same way. Okay, all right. So if you'll look at the domain and range, this is just kind of showing you what does it look like the domain of e to the x is. In other words, think of it this way. Is there anything that any number you can think of that an exponent can't do? Exponents can be negative, right? They can be 0, they can be positive, they can be fractions. Exponents can be anything. So the domain of e to the x is all real numbers, okay? I'm just going to write this in set builder notation. you could do set builder too. So this would just be set of x. X is a real number. You can use that abbreviation I taught you. It's just any real number. So what that means is, what's going to happen on this is the domain of e to the x is going to change into the range of the ln, since they're inverses. Okay, domain becomes range, so that means this is going to be set of y, such that y is a real number. They're the same thing. It's all real numbers. It's just domain is x and range is y, like we've learned. Okay. Now look at what the range is. Look at the red graph. Okay, what does it look to you like the range is? Where to where? 0 to infinity, right? Okay. So what we'll have on this is the range on this is going to be set of y such that y is greater than 0. Now it's never going to be equal to 0 because you've got the x-axis is horizontal asymptote. Well, what that's going to mean is the range of e to the x is the same as the domain of the log. So that will be set of x with x greater than 0. Okay, so what happens on this, since they're inverses, see how they change? Okay, and if you look at the green graph, that's definitely what it says. You can tell the domain of this green graph is positive numbers, right? And you can tell the range of that green graph is all real numbers. It goes from negative infinity to infinity. So they just basically go backwards like we've learned on inverses. That's the idea. Okay, does that make sense? Okay, all right. If you're going to learn logarithmic graphs, you have to understand how exponential graphs go, because they're inverses of each other. That's the idea. Okay. All right, let's do one more here, and then we'll take a break. This section's got a lot of stuff in it, so I want to go through a couple of more graphs on this, then we'll finish up with some log equations after we take a break. Let's go ahead and go through this one. So first of all, we're going to graph this. Now you could do this on a graphing calculator. Let me just ask you a simple question. What do you suppose the x minus 3 does to that log? We just did the log graph. That's the one that did this. Yeah, it goes to the right 3, exactly. So we've done all this, work this semester on talking about transformation. So it's going to just basically everything's going to move to the right 3 of the left graph, or the graph we just did. Okay, so what we're going to do is we're going to find the inverse of this. So we're going to do exactly what we did in the inverse section. First thing you do is when you find an inverse of a function, you just write it down. What do you do with the variables x, y on an inverse? You swap them. Okay, so we do that. So this will become x equals, and I'm going to write the ln as log base e, y minus 3. Okay, just so that you understand that the ln has a base of e, all right? Now what you have to do is you have to write this in exponential form. So you would say e to the x is equal to y minus 3. Okay, so you got to rearrange your log into an exponential form. Then what you can do is add 3 to both sides. You can do that in your head. So you get e to the x plus 3 is equal to y. So that means f inverse of x would be e to the x plus 3. Now that's an e to the x. What does the plus 3 do? It shifts the whole thing up 3. Okay, so that's what happens. That's your inverse on that function then. Okay, so what we'll do with this then is we're going to go ahead and just make a graph. We're going to really just do a transformation. I'm going to zoom out on this a little bit. And all we're going to really do on this is take the green graph and then just shift every point to the right 3, okay? And then this is what's basically going to happen on this then. So I'm going to just kind of write a note to myself like this down below here. And you can do this all in your head, but I'm going to just have you write kind of a little table here. So we have x, we're going to use 1 over e squared, 1 over e, 1 e and e squared. I'm just rewriting the table that I have up here. Okay, and this is y equals ln of x. So this is -2, -1, 0, 1, 2. All right, so what we're going to essentially do is just move everything to the right 3 and approximate it. Okay, so what's going to happen on this when we graph ln of x minus 3, it's going to go like this. the y-axis, which is a vertical asymptote, is going to move over 3. So you just move over 3, and then you want to put like a vertical asymptote there. And then all we need to do is probably just move a couple of these points to get the idea. Like, for instance, this point right here, when you move it to the right 3, that point is going to become 4, 0. I'm kind of making a little chart the way that I showed you how to do for transformations. And then that point, we'll plot that as 4, 0, like that. And then this next point is, well, E is about 2.7. If you add 3 to it to move it to the right 3, then you would end up getting about 5.70, okay? So just move over 5.7, not 0, that's 1. Okay, the y value stays the same, so it would go kind of like that. And that's good enough for a sketch. You've got 2 pretty good points, then the rest of it would go like that. So it's basically the last problem, but everything is switched to the right 3, okay? If you went through and did the other function, what would happen on it is basically if you did the inverse, it would just be e to the x, but everything would be up 3. And I'm not going to do that on that problem, but you could, okay? So if you look at the domain on this, okay, so let's look at what the domain of the log is. What does it look like the domain of that graph is? Where to where? 3 to infinity, right? Okay. Remember what we did before is you set that argument greater than 0. So if you set x minus 3 greater than 0, you get x is greater than 3. So that means the domain, I'll just write this in a set builder notation again. So we would just say set of x such that x is greater than 3. So what that's going to mean is that's going to turn into the range of the inverse. So the range of the inverse is going to be set of y with y being greater than 3. Okay, and that's what that, on that inverse, e to the x plus 3, everything moved up 3. So those things are always the same. Okay, the range is all real numbers. The range of a logarithm is always all real numbers. So this would be set of y such that y is a real number, and then the domain of the inverse would be the same thing. Okay, so you would end up having set of x such that x is a real number. Okay, so the thing you want to understand is since they are inverses, they just change that way. Domain of f becomes range of inverse. Range of f of x becomes domain of inverse. So just backwards because we flipped the variables to begin with. That's why. Okay, so that's the idea with that. That's just got a transformation in it. Any question about that? Now, ln, you could put ln of x minus 3 in your graphing calculator. We'll get to a point, I'll show you in a little bit how you can do, any of these on the calculator. But if you just put in what we just did, ln, I'm going to do this actually, ln of x minus 3. And then if you put in the inverse that when we crunch that out, we got e to the x and then plus 3. Like that, and I'll just do that in a standard window. I'm just doing this so you kind of see what's going on. That's your log, that's your inverse. And if you did y equals x, just to kind of look at the symmetry that I showed you, then it would go like this. So that looks like it's symmetric about that line y equals e to the x anyway. One thing about your graphing calculator, sometimes are misleading. The logarithm goes on forever. It doesn't start there. I mean, you have an asymptote, so it's going that way. So you got to understand how things work. Your graphing calculator can fool you a little bit if you're not paying attention to it. Okay, so that's the idea. All right. Is there any question about that? Okay. All right. Well, let's go ahead and take a break here till about 9:05, and then we'll come back and we'll finish this section up, and then we'll get into the properties of logs today also. Section here. So this one, on log base 3x, I want to show you how you probably the simplest way to learn how to do this is actually to work with the inverse, get that graphed, and then flip the points. Okay, it's easier that way. So the first thing is you will want to know immediately what this inverse is. I'll show you how the inverse goes on this. So you would start off by doing y equals log base 3 of x, and then you switch the variables. So you would end up having x equals log base 3 of y. Of course, then you just do that in exponential form. So you would have 3 to the x is equal to y. So the inverse, and you don't have to go through all that business to get that. You want to know that the inverse of log base 3 of x is 3 to the x. Now what we're going to do on this is we're going to make a table of values for 3 to the x because it's easier. Then we're just going to flip the points. Okay, so when you're doing a graph of 3 to the x, well then you can use these basic points. An exponential, x is an exponent, so it can be anything. So you just kind of do this, 3 to the 0, 3 to the first, 3 to the second, 3 to the negative 1, 3 to the negative 2, like we've been doing. So you just crunch out each of those powers of 3, which you can do all in your head. So that's 1, 3 to the first is 3, 3 to the second is 9, 3 to the negative 1 is a third, 3 to the negative 2 is 1 over 9, like that. So see, it's easy to make the table of values for 3 to the x, and since you know that they're inverses, now all you got to do is just change these backwards. So you'd have 1, 9, negative 2, 1 third, negative 1, 1, 0, 3, 1, and then 9, 2, like that. Okay, to me, that's the simplest way to learn how to do a basic log graph is do the inverse and then flip the points. So then all we're going to do on this is we're only going to graph this logarithm function on this, so just plot your points. So you'd have 1, 0, you would have 3, 1, you would have 9, 2, and then these are just fractional values. So what would happen is your logarithm's going to approach the y-axis. It's not going to touch the y-axis, but that's how that graph would go. So that would be the graph of y equals log base 3 of x. Okay, that's the simplest way to learn how to graph a log is just do the exponential, the inverse, and then flip the points. Okay, it's easier that way in my opinion. Okay, because what happens to students a lot of times when they're doing this like on a test or something, when they're doing a table of values for the log, they don't use these points. And if you're using a log base 3 of x, you want these to all be powers of 3, see? You know, if they're all powers of 3, don't just use any old number because you won't be able to figure it out. Okay? So the next thing is the domain. If you look at the domain of the graph we did, that's all positive numbers. Okay? You've got just x has to be greater than 0. Okay, so we're going to do the domain of the log function is set of x. X is greater than 0. The range is all real numbers. You can see that the graph's going forever to negative infinity. It never levels off to like a horizontal asymptote. It just gets bigger forever. So the range of the log function would be set of y with y being a real number. Okay, and then this is what we've been doing over and over again is if you want to find the range of the inverse, all you got to do is carry over the domain of the function, and that becomes the same. The range of the function becomes the domain. So those things just carry over, except you change the variables. So this just becomes a set of y with y greater than 0. Okay, and then this one would just end up being, since it's domain, it would be set of x, where x is any real number. Okay, so that's how you would get those things figured out, is just switch the domain to range and range to domain on the inverse. Okay, so that's how you do that. If you were going to do like a graph of log base 5 of x, you just want to graph 5 to the x, and then you want to flip the points. That's the easy way to do it. Okay, does that make sense to everybody? Okay, all right. You do it that way, you aren't going to mess up with that. Just do the inverse, and then that'll help you a little bit. Okay, any questions about anything with that? Okay, we're not going to do any real difficult graphs on this. We're not going to do a whole lot with the transformations on this. Just want to kind of get the idea of how it relates to its inverse. The last thing that we want to do is solve some equations, some log equations and exponential equations on this last page here. The log equations we're going to do on here are pretty straightforward, as are the exponential equations. So what you want to do, these are all log equations. You're solving for x. So what you typically want to do is isolate the log. Now what I mean by that is like if you had something like 1 plus, you don't have to write this down, if you had like 1 plus log x equals 10, well the first thing you would want to do is you would want to isolate the log. Why am I doing that? I think I'm thinking ahead. There we go. Okay, so I mean you would want to isolate the log. All these three examples I'm doing here, they're already isolated. So then what you do is you write an exponential form. So in exponential form, this would just be 2 to the third is equal to 2 to the x plus 1. And then you solve whatever equation you end up with. In this case, it's just a linear equation. So this would be 8 equals 2x plus 1. And then you could solve this one from here. You can subtract 1 from both sides. That would give 7 equals 2x. Then you can divide by 2. So you would end up getting on this, you would get x is equal to 7 over 2. Okay, like that. That's a real simple log equation. Okay, the next one's the same way. The log's already isolated. So step 2, just write it in exponential form. So that would be x to the third is equal to 1 over 8. Okay, what do you do to both sides now? Cube root, right? Okay, so you're going to do the cube root of both sides. Okay, and if you do that, you'd have x. Then the cube root of 1 is 1. The cube root of 8 is 2. So that would be x equals 1/2. Okay, and you can check these things, you know, just by plugging in and working out the details. The next one, again, the log's isolated. So you would go write it in exponential form. So that would be 5 to the second equals x to the second plus x plus 4. So see, that's a quadratic equation. So you're going to try to solve this either by factoring or quadratic formula if we have to. So this would be 25 equals x squared plus x plus 4. Okay, what do you need to do next? Subtract 25, get one side equals 0. That's the thing that you always do with your quadratic equation before you start trying to factor it. So that would give 0 equals x squared plus x minus 21. Okay, and then from here you'd have to go to the quadratic formula. That one doesn't factor, so you just have to put this in the formula. So let's do that. So in this problem, A would be 1, B would be 1, C would be negative 21. Okay, so we just have to go to the quadratic formula. So it would be negative B plus or minus the square root of B squared minus 4AC all over 2A like that. All right, and then this one I don't think there's going to be much you can do with this. It'd be negative 1. If you worked what's under the radical, you would have 1 plus 84 over 2. So that would just be negative 1 plus or minus square root of 85 over 2. Okay, so you can end up getting two answers on a log equation if it ends up being quadratic. So that's how that would go. Okay, so each one of those equations we solved are things we've done in our background and done this semester. It's just a matter of rearranging the log to an exponential form. That's the idea. Okay, all right, I'm not going to do anything real exotic on these things. The last thing I want to show you is exponential equations. There's more than one way to do these. In this section, they're designed so you can just write them in log form to get the answer. So what we'll do with this is you always want the exponential isolated. So if you, in this case, it's already isolated. If you had something like 2e to the negative x equals 10, and you don't need to write this down, but you would start by isolating that exponential, okay? So this one's already isolated. So then what we're going to do is these problems are designed so that you can just write them in log form. So if you write them in log form, it would go like this. This is your base, so that goes there. Okay, the answer to a logarithm is always whatever the exponent is. Then that would be 1/3 like that. So that's just taking that exponential form and writing it back in a log form. So instead of writing log base e, write ln of 1/3 equals -2x. Okay, then just solve for x, and then you got the exact answer to the problem. We don't want to get a decimal on this. We just want to get an exact answer. So you could divide both sides by -2. So you would get x equals ln of 1/3 over -2 is the exact answer to that problem. Okay, all right. So that's how that one would work out then. All right. Any question on that? Okay. We're not going to do the ones where you have to get an approximation on in this particular section. So if you look at this second example, what's the first step that you absolutely have to do? You got to divide by 2. You got to isolate the exponential. So you got to, pay attention to that. So you're going to start by dividing by 2. So what you'd end up having then is 10 raised to the 2 minus x equals 5 over 2. And then just write it in log form. Okay, so it goes like this. When you write this in log form, the base is 10, so that becomes your subscript. Remember, the answer to a log is always the exponent. So the 2 minus x goes there, then the 5/2 goes there. Okay, like that. And then what we do is we just solve this for x. Okay, so if I solve this for x, what I would do is probably just move the 2 to the other side. It would be better if you write it as -2 plus, and then the log base 10 can be written in the abbreviated form. You just write log 5/2, and then that would be equal to -x. Okay, so really you can either divide by -1 or you can multiply by -1. It's your call. It doesn't matter. It's the same thing. So I'm just going to multiply the entire side by -1. So what I'd have is +2 there minus log of 5/2 is equal to x. So that would be the answer to the problem. Okay? So that's why I'm going to have you do this type of exponential equation at this stage. Okay? We're going to look at some other ones in a future section that are a little bit different than that. Okay? So the equations won't be too bad in this section. All right? Any questions about anything so far? Okay? All right? The key thing when you're working out stuff in this section is really get a good handle of being able to do logarithms, as many of them as you can in your head, to be able to evaluate them. And you will work with logs pretty significantly in a Calc 1 class, quite a bit actually. You'll learn about the derivatives of exponential and logarithmic functions. All right, any questions about anything that I did on that last page? Okay.